I mean, I'm not opposed to the idea. Like they can do whatever they want. I mean, they can't do whatever they want. That doesn't work with little kids. But you know what I'm saying. Sorry. Will to power. We're gonna take a brief break from chemistry to talk about Freudian. No, Marx. Who's will to power? Nietzschean philosophy, right? I don't actually know what I'm talking about. I'm not a humanities teacher. Ventnor would know.
I'm too brain dead to think if I remember it.
Did you guys take sociology or psychology to learn about Friedrich Nietzsche? No? Okay. Well, I did, but it was a long time ago, and I wasn't a very good student at the time. Or now. Okay. Well, today we're going to talk about concentration, and I feel like if I were Calford, I would have some sort of witty pun about how everybody concentrates in chemistry class, or concentration is hard on a Monday, or well, it's a Monday. May not be Monday, but it's Monday. You know what I mean? Like Monday's a holiday, Tuesday's your Monday.
I mean, in my auto class, it felt like a Monday.
Oh, it feels like a Monday. Does it not? Does it not? It does to me. Anyway, so in chemistry, what do we mean by this term? God, I hate sitting to teach. Can you imagine having to sit in one spot for 75 minutes at a time? Just one spot, no getting up and moving, just stuck there behind your desk like some kind of caged bird, like some kind of animal held in a menagerie for people to gawk at and stare at and point at, and unfree to spread your wings and move as you like metaphorical wings. I mean, maybe you have real wings. I don't know. I haven't checked. But anyway, yes.
I'm just going to relate concentration to density of something.
Okay, that's a related concept, so I like it. So talk to me. When you relate it to density, how would you do that?
Okay. So when you say concentrated, it feels like it's pinpointing one exact spot.
Yeah.
And putting density on that spot so it becomes concentrated.
Okay. So lots of stuff in one spot? Yeah. I mean, yeah, that's related. Absolutely. Now, density, I'd never thought of this comparison, but it's actually a really good one. Density refers to, at the atomic level, how much stuff is in a given space. Concentration is very similar, but it relates specifically to solutions. But other than that, it's very much the same thing. Concentration of a solution is a ratio. You'll find that just about everything in chemistry is a ratio. We love ratios. And it's a ratio of, it's going to be an unsatisfying ratio. Now those words mean almost the same thing. So I never write it like that. I always say like this. And maybe this is why, I wasn't a very good student. Now you can actually see it based on this, why it's useful to have names like solute and solvent, but all the same, I actually do prefer this. When we talk about the solute, we just mean how much stuff. And then when we talk about the solvent, well, all we mean there is how much liquid the stuff is dissolved in. Anytime we make a ratio like that, we're measuring concentration. What units could this be? Well, it could be, and you're going to see all kinds of different concentration units. Anyone in my bio class, do you remember what we measured the concentration of sugar in? Stupid collection of units when we did our little sugars lab. Hello.
Hey, Miss D and I were pondering, we couldn't figure out what date is the movie field trip.
Why, I'm glad you asked.
Oh, we can have a slip for that.
Yes, you most certainly. There you go. And I'm going to make some more copies, but anyone who's interested, send them our way.
Sounds great.
Does anyone remember that? We did a sugars lab, and we added... Does anyone remember we ranged between 0 and 15 grams in 100 milliliters? Well, that was a stupid way of measuring concentration, but it is a concentration measurement because grams is a way of measuring how much stuff, and milliliters is a way of measuring how much liquid it's in. Does that make sense? So that was a concentration unit. It was a stupid one, but it's legit. Sometimes you'll see grams per milliliter. Sometimes you'll see kilograms per liter. Whatever. But given that this is a chemistry class, how do we want to make a habit of measuring how much stuff? What's a better way if we want to relate it to chemistry, if we want to relate it to equations? Moles. When we talk about how much stuff, we could measure how much stuff in moles. And that is indeed the preferred way. This is how it's done. So this is what we call the SI, or the standard unit of concentration. Système International. It's a French-based organization who work out the international units. So when it's chemistry specific, we use something called IUPAC, which is the International Union of Pure and Applied Chemistry. And they decide what stuff is called and things like that. But when it comes to units, units are all managed by SI, Système International. They used to, until about 20 years ago, have all of the actual things. In other words, they had the actual kilogram, which is to say they had a piece of metal that they kept in a vault, and it was a kilogram. And that was the official kilogram. That's what everything was compared to. And then they also had an official piece of metal in a vault that was the official meter, and it was a meter. And that was the definition of a meter. We've since changed that. All of these things are now based on universal properties. The meter is defined as the amount of distance traveled by a certain type of radiation in a certain amount of time in a vacuum. But and like the second is now defined as the time it takes an electron to travel in a vacuum from one spot to another. But all these things used to be physical objects, and SI was the holder of them. And so if you were building a really precise scale, you could actually take your really precise scale to SI, and you could calibrate it using the kilogram or the gram. They also had like the milligram and things like that. And then they would send copies. They would have copies of that made in-house and send that out to other local places that manage these in sort of key places around the world. So like Washington had a big depot of these things. They still do, in fact. It may seem silly, but you trust that when you put something on a scale, it's telling you a number that's real. But how is that thing calibrated? Well, it has to be calibrated against something else. Well, how is that thing calibrated? Well, against something else. Do you know what I mean? I calibrate our scale by making it empty, then putting a 50-gram weight on it, then putting a 100-gram weight on it. But my calibration's only as good as those weights, right? So how do we know those weights are what they are? Anyway, as always, you'll be shocked to hear this is not actually what today's lesson is about. So shall we get back to it? The unit of concentration is moles per liter. And this is also referred to as molar, or big M. Now, this is big M, the unit, not big M, the symbol. If you remember big M, the symbol, like if we talked about the big M of NaOH, what does that refer to? That's right. So the symbol M means molar mass. You don't necessarily need to write this down, but I'm just going to remind you. And that would be measured in grams per mole. Does anyone remember sodium hydroxide? It's a fun one because it's like a rare round number. Yeah, it's 40.0. You don't need to know that. Just thought you might remember. On the other hand, if we talk about the concentration of sodium hydroxide in a solution, it could be 3.2 moles of sodium hydroxide in every liter, which could also be written as 3.2 molar. This is not the symbol M, this is the unit M, is molar, which means moles per liter. It's a little confusing at first. Does that make sense? This is the symbol C, which stands for concentration. Big C. Does anyone know what little c stands for in science? Speed of light in a vacuum.
Constant. Oh, constant. Okay.
Yeah. Anyway.
Yeah, I'm in physics and I don't know that symbol.
Anyway, that's okay. So you're going to hear molarity used interchangeably with concentration. Concentration is a general term, any measurement of how much stuff and how much liquid. Molarity is concentration in a specific unit. That might be worth noting. This is a general term. And this is concentration measured in moles per liter. Okay, so let's actually do the question here. Can we find the concentration or the molarity of a compound given how many moles of stuff we have, given N? So here we have 2.48 moles of sodium hydroxide dissolved in 3.42 liters of water. I don't want you to think of this as a formula. I want you to think of concentration as this ratio. So if we find the concentration of sodium hydroxide, we'll just remind ourselves what these mean. The first thing I'm going to introduce you to is another system you'll see all the time, which is this. The square brackets also denote concentration. If we write something in square brackets, we mean the concentration of. You've probably seen that in writing at various points, especially if you've taken bio, it came up a bit. And maybe you've known what it means, maybe you haven't. But that is just a short form for concentration. All right? And just going to be stuff in liquid. That's what concentration is. How much stuff is in that liquid? Does that make sense? Don't memorize as a formula. Concept. What's concentration? It's how much stuff's in the liquid. And what are we going to measure stuff in? And what are we going to measure how much liquid in? Awesome. Okay. In this case, how much stuff? 2.48 moles. Yep, beautiful. So we can just put that here. We have 2.48 moles. Moles of what? Very good. And how much liquid do we have? Yeah, 3.42 liters. And if we wanted to put anything there, we could say solution. I probably would just put liters. But it's not liters of sodium hydroxide. Is sodium hydroxide a liquid? No. So you could say solvent if you wanted to. Again, by convention, we usually just leave this blank. Does that make sense? But what you shouldn't put is this, because that's actually not true, right? You don't have 3.42 liters of sodium hydroxide. Sodium hydroxide is a solid, not a liquid, before we dissolve it. And when we dissolve it, it'll be 3.42 liters of sodium hydroxide solution. I suppose you could put this if you really wanted to, but why bother? Does that make sense? Usually we'll just leave it as liters. If we have more than one solution, sometimes what we'll say is liters of solution A, liters of solution B, liters of solution C, or liters of solution 1, just to keep track of which is which. Does that make sense? In this case, I'm just going to leave it like that. And then we can do the math. This should be on the order of 5/7, which is, are we talking like 0.8? Can somebody do this math for me? Like high sevens, 0.7. Oh, low sevens. That's what I meant to say. What is it? Is that enough sig figs for us? How many should we have? Can I get one more? Oh, I'm sorry. Did you say it and I just didn't hear you? I'm sorry. I should have known that you'd know that. And then our unit could be moles of sodium hydroxide per liter, but we don't need to write it that way. We can write that as 0.725. And then what's the short form for moles per liter? M. M as a unit. Again, not as a symbol, but M as a unit means molar, and then we could just say that, and that means moles per liter. Occurs to me I had the answer on my screen over here. I could have looked really smart if I just looked at it and been like, oh, I think that's going to be, I don't know, 0.723, 725 maybe. I don't know, something like that. Didn't think of it. I would never do that, by the way. I have too much ego about my mental math skills, even though I clearly shouldn't because I've been nothing but wrong lately. But that's okay. I'll get there. Okay. How's that feel? Not too bad? Pretty straightforward? Take the moles, divide it by the liters, you get moles per liter. That is molarity. That's the concentration. Easy, 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 right? Simple, almost trivial, maybe too easy, a little boring. How much stuff divided by how much water, that's concentration. All right. Let's look at the next one and see what we can do. Here, we're going to find the concentration of this many grams of sodium hydroxide in that many liters, but still using moles per liter. So what do I do here? Well, here's what you could do. If we were in my grade 11 chemistry class, we'd have done a set of calculations, converted this to moles, and then did what we did up above. But I'm not going to teach you that way. You know why? Because we're efficient, damn it. Because what tool do we have that we use all the time for math and chemistry? Dimensional analysis, and it's powerful. So we're going to use dimensional analysis, and I'm going to give you a new rule. We're going to use dimensional analysis. And then we're going to make note. If the answer is going to be a fraction, start with a fraction. And when I say the answer is a fraction, I mean the unit. A fractional unit, like moles per liter, or kilometers per hour, or what's another one? Or chicken sandwiches per student. So you know how we've always started with a number and then multiplied by a fraction in dimensional analysis? Well, that's because we've never used dimensional analysis yet to get an answer that was a fractional unit, where we wanted a top and a bottom unit. But in this case, our answer is going to be in moles per liter. Does that make sense? Which means our answer is a fraction, and if your answer is a fraction, you want to start with a fraction. And so I guess I will go one step further. This is still sodium hydroxide. Is that true? This is not erasing because it hates me. That's why. So how would I say concentration of sodium hydroxide? By the way, there's two ways. Which one? What are the two ways? I just want to use a symbol here to say concentration of sodium hydroxide equals, just so I look good, fancy. Yep. Yeah, I could do it in square brackets, and what would go inside them? Like the actual formula, which in this case is NaOH. What was the other way I could have written it? Yep. Yeah, big C or little c? Big C, good. I'm going to go with this one. And we're going to start with a fraction. We're going to lead with a fraction because our answer is going to be a fraction. So if I'm leading with a fraction, what goes on there? Well, remember, what's concentration? What goes on the top of our concentration? How much? Stuff. And what goes on the bottom? And if it's helpful to you, you could actually just write that. Stuff over liquid. You're not going to be writing that for long because it's kind of silly. But here we go. In this case, how much stuff do we have? Even though it's not in moles, we know how much stuff we have. How much? Yeah. And if you hate scientific notation, I could change this by doing what with that decimal place? Moving it 1, 2, 3 places, right? If you like that better, that's fine. If you like the scientific notation better, that's fine too. I don't care which. And how much liquid do I have? 4.12 liters. Now, I could calculate this, and I would get a concentration, but what would my unit be? Grams per liter. Do we want the unit grams per liter? We are going to consistently use what unit for calculation, or for concentration? Moles per liter. So, we know how to do this in dimensional analysis. Do I like the liters? Is it good? Is it where it should be? Can I just completely leave it alone? Sure. What don't I like? Grams. So if we want to get rid of grams, we're going to multiply this by a fraction. And how do I get rid of grams? Right now it's on the top, so where do I need to put it in this next fraction to get rid of it? The bottom. Bless you. And what do I want on the top instead? I don't want grams per liter. I want moles per liter. Well, wait a minute. We know where to get this. How do we know how many moles of sodium hydroxide are in a gram? Or if we prefer, how many grams of sodium hydroxide are in a mole? Periodic table. So we could do that, and we could really quickly work this out. You might even remember this one. We actually talked about this one just a few minutes ago of what its molar mass is. But in case you forget, how much does sodium weigh? Does anyone have a periodic table on them? Did I say periodic? Speaking oddly today. How much? Sure. And how much is oxygen? And hydrogen? And what's that all add up to? Very good. So that's easy, and then I can just put that in here, and we're good to go. I'm pretty sure I put them exactly where I meant to put them. I should probably swap them. Why is that?
Because there's not just 1 gram in 40 moles.
Yeah, that's not true. So 1 mole, on the other hand, does in fact weigh 40.0 grams. Awesome. What units will cancel? What units remain? Moles on top and moles per liter. Am I done? I mean, obviously I need to do the math, but am I done canceling units? We want moles per liter. All right, so that's going to be a good unit for us because we have moles of sodium hydroxide per liter. Now we just need to do the math. This is very close to being 1,000. And 1,000 divided by 40 is very close to being 25. This is a little less than 1,000, so it's going to be less than 25. I'm going to bet 22, 23. Anyone? Get a calculator. Get a calculator. Don't be lazy. Don't wait for someone else to do it. Go get a calculator. Stand up. No, don't look at your phone. I didn't tell you to use your phone. I said go get a calculator. How'd I do? I said like 22, 23. Great. Now, how many sig figs should we have? How many sig figs here? That's this number here, remember? So 3 sig figs there. How many sig figs here? How many sig figs here? Great. And how many here? How many sig figs there? Yeah. Don't all speak up at once. So how many in my answer? Great. And what was it? 23.4? Perfect. And what's another way to write that? Well, we could say the concentration is 23.4. I could just write moles per liter of sodium hydroxide again, but what's another way we often represent that unit? Big M. And how do we say that? How do we speak that aloud? Molar. So 23.4 molar sodium hydroxide. And molar sodium hydroxide means a concentration of 23.4 moles in every liter. How's that feel? Not too bad? Worst thing ever? Now listen, you might get some stupid, annoying, dumb units. Can happen. Let's look at nuts. They might be nuts. Here we want iron 3 sulfate. Oh, wow. And for some reason, I have opted to just put the numeral 3 in there. Is that what I should be doing? Tisk, tisk, Orlando. All right. How would I find the concentration of, first of all, what is iron 3 sulfate? What charge does iron take here? Right, and what is sulfate? SO -2. So what's the formula of this stupid thing? Does it work with 1 of each? Does it work with 2 of each? Does 3 get us there? Fe2, open bracket, SO4. Very good. It's annoying. So we want to find the concentration of iron 3 sulfate. Trying to write the numeral 2 while saying the number 3 aloud. Challenging. All right. Our answer to this is going to be concentration. What is the unit of concentration? Concentration is measured in what? Moles per liter, which is a fraction. So this answer will be a fraction. So what should we do? Start with a fraction. If your answer is going to be a fraction, start with a fraction. And if we're dealing with concentration, what goes on the top of that fraction? We got two numbers here, milligrams of iron sulfate and milliliters of water. Which one of those do I put on the top of the fraction? Yeah, why is that? It's how much stuff. All right, so I'm just going to put it as it is, 7.2 milligrams of Fe2SO4 3. God, I hate when they're long units, but there we are. And what goes on the bottom? Very good. And now we're in good shape. The only problem with this is, well, there's two problems. The first problem is that instead of moles, we're working with grams. And that's even worse because it's not even grams, it's milligrams. Okay, well, let's get to it. Do you want to deal with the milligrams or the milliliters first? Because we don't want any of these to be milli, right? So I don't want to talk about milligrams. Where should I put that? On the bottom. And instead, I just want to talk about grams. Well, how do I do that? How many grams in a milligram, or how many milligrams in a gram? Is that true? First of all, what's milli mean? No, it's a number. It means? That's okay, one thing at a time. He's testing me, and I passed the test. So first, milli means 1,000. So it would be 1,000, not 100. But then, is it true that if something weighed 1,000 grams, it would weigh 1 milligram? No, that's obviously silly. So what do I have to do with those two numbers? Switch them. Is it true that something weighed 1 gram would weigh 1,000 milligrams? Yeah. Okay, now, if I stopped calculating now, what would my unit be? Grams per... Okay, do I want milliliters on the bottom? So what can I do next? We've never canceled something on the bottom before. How are we going to do that? Ah, good. If it's already on the bottom, to cancel it, we'd put it on the top, right? Those will cancel. And what do we want on the bottom instead? Not milliliters, but liters. What number makes this true? We just said milli means 1,000, so that's easy. I'm pretty sure it is. I just told you that milli means 1,000. It comes from the Latin. Do you know that in some English-speaking countries, they don't use the word thousand, they use the word milliard. They have milliards and millions. Yeah. So anyway, there you go. So that's your etymology lesson for the day. We can move on. 1 milliliter is 1,000 liters. Pretty confident that 1 milliliter, if I had 1 milliliter right now, I could say, if I drank it, I could say that I drank 1,000 liters. That would make perfect sense. if all I did was drink 6 liters a day by drinking, like 0.006 milliliters, yeah, I would not do well. Okay, so that's correct. 1,000 milliliters is 1 liter. All right. What units cancel now? The milliliters cancel. And if I stopped calculating now, I would have grams per... We're almost there, but we don't measure in grams per liter. We measure in what per liter? Moles. So I've got to get rid of grams. Where is it right now? So how am I going to cancel it? Put it on the bottom. And what do I want on the top? I don't want grams per liter. I want moles. And this, we're going to have to work out because I actually don't know how much a mole of this stuff weighs. But I bet we can figure it out. The molar mass of Fe2SO4 3. Okay, we can do this. How many irons? And are they 55.85? I was going to say 845. Oh, that's the same. Okay. And then how many sulfurs do we have? 3. Good. And each sulfur weighs how much? 32.07. And finally, we have how many oxygens? 12 of them, and they each weigh 16.00. And all together, that's going to be a lot. It's a pretty heavy compound. 112 plus another 96 is 208. And then plus another 160 is 368, plus another 32, 398. This should be close to 400 exactly. Is that right? That seems convenient. That doesn't feel right. Somebody do that for me.
You're just there. Holy crap, you were just there.
Yeah, 399.9. All right. A redeeming one. And that, don't forget, we actually have a 0. We do have a second decimal place here, so let's use it. Because remember, when we count sig figs for adding, it's not based on sig figs, it's based on decimal place. So we have a second decimal place in all these, so we can have a second decimal place there. All right. So I can put that number here, and you'll all be pleased to see that I'm not even being silly about it. I'm just writing it in the fraction, even though it pains me to not be silly. Thank consolation, at least I wrote incredibly messily, so that's a form of silliness. Is it 9-1? Oh, that's weird. I trust you. I wonder why my calculator didn't show that. That's odd. And I probably should put grams. That'd be good. Okay, what units cancel? Grams of iron sulfate, iron 3 sulfate. And what units will remain? Moles of iron sulfate per liter. And this math, if we can get on that, oh God. Well, the 2000s cancel each other, so that's nice. It's going to be real small because that is going to be 3 times bigger, which would be 1200, and then another 10 times bigger than that, which is going to be 12,000. 7.2 divided. This is going to be like times 10 to the negative 4. I'm going to need to put this in my calculator. How would I plug this into my calculator? In fact, I'll do it up here on the screen so we can all see what we should type in. We're getting to some long dimensional analysis now. What do I type in? What do I start with? I resent you all. That includes you, Rick. What do I start with? What's the first number on here? 7.2. And then what's this operation? Divide by 36.7. Now listen, if you're clever, you could note that times 1 divided by 1,000 times 1,000 divided by 1. We could just ignore this whole section number-wise, but I'm going to put it. Times 1 divided by 1,000 times 1,000 divided by 1. That's fine. Now we're there. Times 1. And then finally divided by 399.91. And that should give us a total of, now this will only give me 1 decimal place, which is not good enough. But it is indeed times 1, 2, 3 times 10 to the negative 4. So 5 point what or 4 point what times 10 to the negative 4? Anyone? Do this on your calculator? I actually need you to. This 4.9 times 10 to the negative 4. Yeah, I like that. And a better way to write that, because this gets clumsy, is 4.9 times 10 to the negative 4 molar iron sulfate. Iron 3 sulfate specifically. Did I get that right in my practice? Hey, I did. I could have looked at that. Howdy. Well done. Great, right on there. Yes. Sorry, I should separate those out. Yeah, that can go right there. That's okay. I'll sort through it. So you can see the dimensional analysis gets a little bit uglier now that we don't know that sometimes we're starting with a fraction. With a bit of practice, it'll come, I promise. We're going to look at one more example today. And I'm going to leave you with some practice on here. The last example we're going to look doesn't find concentration. We're going to, for the first time, use concentration. In this case, we're going to find the volume needed to prepare a solution. Oh, for God's sake, Joe. Obviously, this is ridiculous. This should say 6.2 times 10 to the exponent negative 3 grams. That happened at amateur 04 o'clock. Also, I said amateur, almost rhyming with hamburger. So we'll call that amateur 05 o'clock. Anyway. All right. This is going to be another dimensional analysis. If your answer isn't a fraction, don't start with one. So in this case, the question asks how much water. What unit will we measure that in? Yeah, this will be liters. Does that make sense? That's going to be the answer. Is liters a fraction? Is that a fractional unit? In math, what we would call a rate. I guess in physics as well. No, it's not like liters per cucumber or anything. It's just liters. It's just a single unit. So in this case, we're not going to start with a fraction. We're going to start with a number, and we're going to multiply it by a fraction the way we've always done dimensional analysis. If your answer isn't a fraction, don't start with one. And here's the nice thing. We have two numbers here. One of these numbers is a fraction, one isn't. Which one of these two numbers is a fraction? Yeah, this doesn't look like a fraction, but actually it is. The reason it's a fraction is because that big M really means what? This really means 0.0500 moles in how many liters? Concentration always tells you how many moles are in 1 liter. Does that make sense? So even though it doesn't look like it, this number is actually a fraction. So is that the number we're going to start with? If your answer isn't a fraction, don't start with a fraction. Our answer is not going to be a fraction, so we don't start with the fraction. So which number do we start with? Yeah, now to be clear, you could actually start with this and still get the right answer. But if you build this as a mental habit, it makes doing dimensional analysis easier. It'll work either way. You can start with anything. You can start with what time you woke up this morning and do dimensional analysis to get the answer to this question. It's fine. Seriously, you could absolutely do it. But we're going to start with our number that isn't a fraction, which is 6.2 times 10 to the negative 3 grams. Sorry? Yes. All right. Now, here is where I'm going to break out a drawing I haven't done in a while. What is the central unit of chemistry? And what symbol do we use to refer to how many moles of something we have? Yeah, a little n. If I know how many moles of something I have, what else can I find out? Well, I could find out the mass of that thing, and we measure that in grams, right? I could also figure out how many particles, but I'm never even going to write that again. You know why? Because I don't care. It's stupid. It doesn't count for anything. But you know what else I can figure out? I could figure out the volume of a solution if I knew the concentration. And on the other hand, if I knew the volume, I could figure out the concentration of a solution. Does that make sense? These are now new calculations I can do. And of course, using balanced chemical equation, what else can I do? I can also talk about something else, right? If need be. And of course, then from each of these, so I'm going to write in blue what you need to know. You just need to know the molar mass from the periodic table for this. For this, you need to know the concentration. I'm just going to write conc. And for this, you need to know the volume. And of course, then we can do it all over again. If you know how many moles of B you have, you can figure out how many grams of B you have. If you know how many moles of B you have, you could figure out the volume of the solution you're working with. And you could figure out the concentration of the solution. So here, what are we going from? We need to go from grams, and we're going to have to make our way to liters. How do I do that? Well, it's actually not that bad. We start with how many grams of something we have, and what are we going to figure out? How many moles of that thing we have. And then from there, we can just figure out the volume. And what are the two things we're going to need to know to do that? How much this stuff weighs from the periodic table, and the concentration we're working with. Do we know those two things? Well, we don't directly know the mass from the periodic table. Well, actually, sodium hydroxide, so we do. And do we know the concentration? Yeah, it's given to us. Does that make sense? It's actually a pretty trivial question. So first, we're not going to go directly to liters. We're going to go from grams to moles. No problem. I multiply this by a fraction. What unit goes where? Grams goes on the bottom. And on the top, moles. And like I said, we already have this from a previous question. How much does a mole of sodium hydroxide weigh? Yeah, 40.0 grams. In fact, I think it's 2 zeros, if I'm not mistaken. Not that it matters one bit for this question. If I were to stop calculating now, what units cancel? What unit remains? So I'd know how many moles of sodium hydroxide I have. The problem is the question isn't that. The question is, how much water do we need to make this solution? No problem. How do we go from moles to volume? Yeah. So I can actually cancel moles and replace it with liters. But to do that, where's moles going to have to go? And liters? On the top. Because we know how many moles of sodium hydroxide are in each liter, and in this case, it's a water solution, right? An aqueous solution. So I could even say liters of water. I could just say liters if I cared. Well, wait a minute. How many liters of water are in a mole of this stuff? Or how many moles are in a liter of water of this stuff? Yeah. Well, that's what this tells us, right? This tells us that there's 0.0500 moles in every liter. So I can just put that number here, just like that. And I put the number there. I put the number, well, as you can see, the number is 0.0500 on the top and 1 on the bottom. So I put that here. I put units. I put liters here and moles there, so I'm good. I don't know why you're criticizing me. Now you're pointing at me. My mother told me that it was rude to point. She also told me it was rude to raise your voice with somebody, which, of course, you've never heard me do. Yes, that's right. So we do need to be careful because this tells us that there's 0.0500 moles of this stuff in every liter. All right. What units cancel? And what will I be left with? What will I be left with? I'll be left with the volume in liters, and in this case, oh God, I don't know. This is going to be real small. Okay, I can do this. I can do this. I can do this. I can do this. 40 divided by 5 is 8. So that'd be 80. That'd be 0.8, 0.08. So doing 6.2 divided by 0.08. Oh my God. No, 0.8. 0.8. So it's going to be a little bit bigger than that. So it's still going to be times 10 to the negative 3, but maybe like 8 or 9 times 10 to the negative 3. Somebody just do this for me. By the way, when we're putting scientific notation in our calculator, how do we want to make sure we do that? Yeah, which on those calculators you do how? On yours, it's like second function comma, right? In my case, I just put a big old E like that. And then do we put the 10? Do we press the exponent button? Just 6.2 scientific notation button, then the negative 3. What am I multiplying by? 1 divided by 40 multiplied by oh, I was way off. I wonder why I was way off. Oh, anyway, I'm right about my order of magnitude, but I got my number horribly wrong. But that's okay. Won't be the first time, won't be the last time. So if I want to write this in scientific notation, I would write it as 3.1 times 10 to the negative 3. And what's the unit? Liters of water. Is that a lot of liters? No. In fact, it's not even a milliliter. It's real little. The last time I taught this, I asked a student to come up and write their answer, and what they wrote was, mitochondria is the powerhouse of the cell, which was not helpful. So then I obviously had to write the answer myself. I wonder who that was. Whose writing is that? Sorry? I see no problem there. All right. No, I mean, fair enough. My cat's breath smells like cat food. Sure. Yeah, my cat's breath smells like cat food. Answered every question you need. All right. So this stuff, as you can see today, tricky one, we've introduced a brand new concept. The idea of using dimensional analysis to get an answer that has a fractional unit. And if your answer has a fractional unit, what do you have to lead with? You have to start with a fraction. But we don't want to throw the baby out with the proverbial bathwater, which means if our answer isn't going to be a fraction, what don't we start with? A fraction, right? So it's introducing a new thing to think about, which is never a bad thing. What's my answer going to look like? Does that make sense? Now, when you do a dimensional analysis question, one of the quick questions you're going to ask yourself is, what unit is my answer in? If that unit is a fraction, start with a fraction. If that unit isn't a fraction, don't. That's it. You do that and you're good. You've got 9 whole minutes. That's enough to do at least 1 or 2 of these questions, so get on it. Don't waste your time. Don't lollygag.